Imagine driving across a suspension bridge that actively knits its own microscopic fractures back together after a magnitude 7.0 earthquake. Picture dropping your smartphone onto solid concrete, only to watch the shattered glass seamlessly fuse itself back into a pristine surface within minutes. This is not the realm of science fiction, but the imminent reality of advanced materials science. We are standing at the precipice of a revolution where the inanimate world around us is waking up, adopting the biological superpower of regeneration to protect our everyday products from the ravages of time. For centuries, human engineering has been defined by a fatalistic life cycle: extract, build, degrade, and discard. Every skyscraper, airplane fuselage, and microchip is slowly dying from the moment it is manufactured. But a radical paradigm shift is rewriting the fundamental laws of degradation. The emerging field of self-healing materials promises to shatter the inevitability of structural failure. These smart materials are engineered to autonomously detect, halt, and repair damage without human intervention, effectively extending product life cycles indefinitely and drastically reducing global waste. At the heart of this transformation is a deep dive into the microscopic architecture of matter. One of the most promising approaches involves embedding microscopic capsules within a host material during the manufacturing process. These tiny spheres act like synthetic white blood cells. When a crack begins to form and propagate through the material, it ruptures these embedded capsules, releasing a highly reactive liquid healing agent. This agent flows into the microscopic fissure, meets an embedded catalyst, and instantly solidifies, sealing the fracture before it can compromise the larger structure. Beyond liquid agents, researchers are fundamentally altering the molecular DNA of substances through the use of reversible chemical bonds. In traditional materials, chemical bonds are static and permanent. Once broken by stress or physical trauma, they are gone forever. Reversible bonds, however, are highly dynamic. Under specific triggers like heat, light, or even just physical proximity, these molecular connections can break and then dynamically reform. When damage occurs, the severed molecules actively seek each other out, re-establishing their connections and restoring the material to its original integrity. If the molecular science is already proven in laboratory settings, what stands between us and a world completely built from self-repairing infrastructure? The leap from a controlled petri dish to the chaotic, unpredictable environments of the real world presents a staggering set of hurdles. The primary engineering challenge lies in balancing a material's inherent strength with its ability to heal. Highly rigid materials, like the titanium alloys used in aerospace, rely on dense, tightly packed atomic structures. Introducing microscopic capsules or dynamic bonds into these dense matrices can inadvertently weaken the baseline strength of the metal. Engineers are locked in a relentless optimization problem, striving to design repair mechanisms that are efficient and durable under extreme conditions, without compromising the core structural integrity required for widespread industrial use. The most significant breakthroughs thus far have occurred in the realm of self-healing polymers. Polymers are large molecules composed of repeating structural units, commonly found in plastics, rubbers, and resins. Because their molecular chains are inherently more flexible than metals or ceramics, they are prime candidates for dynamic bonding techniques. Innovations in these synthetic compounds are already yielding self-repairing protective coatings for automotive paint, flexible electronics that survive repeated bending, and advanced composites designed for the next generation of renewable energy infrastructure. The inspiration for this leap forward comes directly from the natural world. According to Dr. Elena Rostova from the Max Planck Institute for Intelligent Systems, the goal is not just to build better plastics, but to mimic the resilience of living tissue. She notes that biology has spent billions of years perfecting the art of localized repair, and by translating these biological blueprints into synthetic chemistry, we are fundamentally redefining what it means for a material to be alive. As these biomimetic polymers mature, their integration into global industries will trigger a cascading transformation. Consider the aerospace sector, where microscopic fatigue cracks in an aircraft's fuselage can lead to catastrophic failure. Self-healing composites could autonomously mend these microfractures in mid-flight, drastically reducing maintenance costs and elevating passenger safety to unprecedented levels. In the automotive industry, self-repairing chassis and battery casings could extend the operational life of electric vehicles by decades, fundamentally altering the economics of global transportation. The most profound impact, however, will likely be felt in the very foundation of our modern civilization: concrete. Concrete is the most widely used building material on Earth, but it is notoriously brittle, prone to cracking from water ingress and temperature fluctuations. Researchers are now infusing concrete mixtures with dormant bacteria and starch. When water seeps into a new crack, it awakens the bacteria, which consume the starch and excrete limestone, naturally patching the fissure. This self-healing infrastructure could save trillions of dollars in global maintenance and prevent the collapse of aging bridges and tunnels. What happens to the global economic engine when the things we build simply refuse to break down? The widespread adoption of these technologies threatens to upend centuries of established industrial logic. The integration of these intelligent substances is the critical missing link in achieving a true circular economy. In a circular economy, the traditional linear model of make, use, and dispose is replaced by a closed-loop system where materials are continuously reused and regenerated. Self-healing technologies will act as the ultimate catalyst for sustainable manufacturing. By exponentially increasing the lifespan of everyday products, we can drastically reduce the continuous extraction of raw materials, curbing the massive carbon footprint associated with global supply chains. Yet, this utopian vision of endless durability masks a profound economic disruption. Our current global economy is heavily reliant on the concept of planned obsolescence, a strategy where products are intentionally designed with a limited lifespan to encourage continuous consumption. If consumer electronics, home appliances, and automobiles rarely need replacing, the manufacturing sector could face a catastrophic contraction. The transition to unbreakable goods forces us to question how we define economic growth in a world where constant replacement is no longer necessary. This economic friction is already sparking intense debate among policymakers and industry leaders. According to technology ethicist Dr. Julian Vance from Oxford University, the shift toward self-healing infrastructure will require a total reimagining of global labor markets. He argues that while we will lose millions of traditional manufacturing jobs reliant on disposable goods, we must proactively transition our workforce toward the highly specialized maintenance, monitoring, and recycling of these advanced, quasi-living materials. There is also the looming environmental paradox of indestructible materials. If a self-healing polymer is designed to endlessly repair its own chemical bonds, how do we eventually break it down when it becomes technologically obsolete? The very mechanisms that make these materials resilient could inadvertently create a new class of hyper-durable pollution. Without the simultaneous development of targeted, on-demand degradation triggers, we risk filling our landfills with smart plastics that aggressively resist decomposition for millennia. Despite these terrestrial challenges, the ultimate testing ground for regenerative engineering lies far beyond the boundaries of our own atmosphere. The extreme hostility of the cosmos demands materials that can survive the impossible. As humanity looks toward establishing permanent outposts on the Moon and Mars, self-healing materials become an absolute necessity. Deep space exploration is defined by isolation, extreme temperature fluctuations, and relentless radiation. A micrometeorite strike on a Martian habitat or a deep space vessel cannot wait for a resupply mission from Earth. Habitats constructed from self-repairing composites will autonomously seal breaches in milliseconds, preserving vital atmospheric pressure. These materials will be the silent, invisible guardians of our interplanetary future. The next frontier of this science involves marrying regenerative chemistry with advanced artificial intelligence. Future materials will not just react to damage blindly, they will be embedded with nanoscale sensors that act as a synthetic nervous system. These sensors will feed real-time structural data to an onboard neural network, allowing the material to predict where stress fractures are likely to occur and preemptively route healing agents to those exact locations before the damage even manifests. The deep science of self-healing materials represents one of the most profound technological leaps in human history. We are moving from an era of passive, decaying objects into a future defined by active, resilient environments. From the microscopic capsules hidden within our smartphones to the self-mending hulls of starships, these innovations promise to rewrite the rules of durability and global impact. As we navigate the economic and environmental complexities of this transition, one thing remains certain. The world of tomorrow will not just be built by human hands, it will actively heal itself.